All right, you guys. So for number 11, you really have to be organized in your approach. Okay, this is yet again another sort of exercise that has a lot of different tools that you can use. So you have to be very organized and methodical in how you approach this. Okay, so consider the following diagram, which shows the plan of part of a house. So here we have, as it says, a narrow passageway with width 3 over 4 meters, which is this passageway right there, right? Is perpendicular, okay, that can be useful information, is perpendicular to a room with width of 6. And so just so that we all understand, this is the 3 over 4, right, all along this, and this is the 6 meters of width, okay? Boom, 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 boom. So, that being said, they tell us that at the corner point C, points A and B, okay, are variable points on the base of the walls such that ACB is a straight line. Let L denote the length of AB in meters. And so L actually goes like this. All of this will be the famous L, okay? And alpha, which they actually already put for us, will be the angle that AB makes with the room wall, where alpha is between these values. Okay, so that is definitely going to be more useful down the line. But for now, what interests us is that the angle alpha is this guy right here. Okay, so that being said, for part A, we need to show that L equals that whole thing. Now, before we even move on, whenever you face an exercise that starts with show that, notice this is a fact, okay? So a lot of times in my videos, I make the point that, what you need in part C is something from part B, or what you need in part B is something from part A. So like, if you don't have the exercise like completed thoroughly from the beginning, you might get stuck at some point, right? And then it has something positive and something negative. It can have something positive because looking at the other parts that you just did, it can be a very big hint for what's coming. All right, but another thing that can play against you is that, dude, if you didn't do part A, you can't do anything, right? And so watch out for that. It's not always the case, but you do need to like keep an eye out for that. See? Now something that I've come to realize or that I've noticed is that whenever you have a show that exercise, because it's a fact, technically you can skip this one and only do this if you're low on time, right? Like don't skip exercises just to skip them. Skip them if you're low on time, if you're prioritizing, etc. You don't have to show you don't have to, you can skip part A and do part B, right? Because part B, you need to do the derivative of this equation, and they're giving you the equation, right? So you can do part B without part A. That's what I'm trying to tell you. Whenever you have a show that show up in your exercise, whenever you have a show that show up, that means it's a fact. That means you can use it, okay? And that's also important because down here, this show that, okay, is also a fact. All right. Is that going to be useful or not down the line? I do not know. But watch out. Whenever they say show that and you're stuck on that exercise, like imagine we never solve part A, right? Don't give up. This is a fact. You can do part B. Okay. So even if you have a lot of trouble showing whatever you're supposed to show, know that you can work with it as a fact for the parts that follow. Okay. That's the big hint I want to start off with. Keep it in mind. All right. Now we will actually get into the exercise. See? So we need to show that L equals that whole thing. See? Now there's a lot to go over here, and the main idea is, first of all, L, as we mentioned earlier in red, is that line. So we need to basically find the sum of two things in order to find that line, right? And on the other hand, it has this thing called sec and cosec. And so this is something we also have to go over. What the heck is sec of alpha? Whoop, sec. What the heck is sec alpha and what the heck is cosec alpha? Now, This is the kind of thing that is awfully specific, but it is so specific that it is also in your in your formula booklet. Okay, guys, the day of the test, you're going in with 2 hours of sleep, 2 years of this thing called a graphing calculator, hopefully that you can use, not always, right? Depends on the test, and a pen and pencil, your brain, a whole lot of motivation, and the formula booklet. So the formula booklet is something you can use the day of the test. So get familiar with it. Why is this important? This is important because the moment, and this is what like the level I need you to reach, okay? The moment you read sec or the moment you read cosec, first, you're going to freak out because it's trigonometry and no one understands trigonometry. But secondly, you will recognize it as something that you've seen before. And where have you seen it before? Bada bim, bada boom, in the formula booklet. So, guys, that is how you're supposed to use the formula booklet. Okay, you don't have to know it by memory, but also don't just say, I have the formula booklet, so I don't have to know the formulas. No, no, no. That's not the ideal approach. The ideal approach is knowing what is in it vaguely. Okay, is recognizing that if you read sec or you read cosec, you say, I'm pretty sure that's in my formula booklet. Let's check it out. Okay, that's the sort of thing we need to do. So you obviously go to topic 3, geometry and trigonometry, because if you don't know what's going on, you're probably in a trigonometry problem. So we go ahead and go to page 7 HL only because we are cool kids. We are in HL. So we go to page number 7, and here we can really start playing around with what's happening. So, will you look at that? So here is sec, and here is cosec. Now, maybe the names are a little bit not so intuitive, right? Because sec, you might think about sine because it has an S, or cosec, you might think about cosine because it literally starts with co, but stick to the formula. So really, sec is just like inverse co. You can kind of think about it that way, right? Inverse in a more literal sense because it's 1 over cosine, right? So sec is 1 over cosine, while cosec is 1 over sine. And so that is already a big hint. So if sec is 1 over cosine and cosec is 1 over sine, then looks like I need to use sine and cosine in order to solve this, right? Now, going back to length L, well, length L, they did tell us for some reason, and the IB always tells you things that you need to use. Okay, so for some reason, they just told us, oh, points A and B and C lie on a straight line. Okay, ACB lie on a straight line. And so because they lie on a straight line, that means that length L can be this distance plus this distance. So length L is that plus that. So let's explore piece by piece how we would do it, taking taking into consideration that we probably have to use cosine and sine. So from here, well, how can you find that length in green? See? So eventually, right, if you stare at it for long enough, you will start to realize, I can draw a triangle here. Because it's a because it's a trigonometry problem, once you identify you have sine and cosine going around, you should be thinking in right triangles. Okay, a lot of the tools that you can use in trigonometry have to do with right triangles. Okay, that is why trigonometry has tree with it, tree for triangle. Think in right triangles. That's what I'm trying to tell you. Think in right triangles, and eventually you will realize that you do have a right triangle hidden right over here, right? And so this right triangle, well, what do you know about it? This right triangle, okay? What you know about it is that this is 90 degrees, right? And some of you might be telling me, like, how do you know it's 90 degrees? Well, because this passageway is perpendicular to the room. Haha, got you there, didn't I? So, you know that this is 90 degrees, right? You know that because this distance is 3 over 4, that means this one up here as well. So this is 3 over 4. You know that because this angle is alpha, The one on the other side is also has to be alpha, so this is alpha. And is that all I know? I think that is all I know. Yes, that is probably all I know. See? And so this thing in green is from A to C, right? So we can just call it AC. All right, cool. On the other hand, we do have another triangle over here, right? Once we start thinking in right triangles, it's very easy to spot because this is 6 meters. Then that means that if you keep moving this line over and over and over, eventually you reach this guy here. And so bada bim bada boom, it's a right triangle. It's a room, right? So it's nice dimensions. This is a 90-degree. And so what do you know about this triangle? You know that this is 6 meters. You know that this angle is alpha, and that from here, right, from here to here, you have the distance CB. And so if you actually redraw that triangle, what you end up with is, just so that we're all on the same page, you know that this is 6, and you know that this line in blue, right, this line in blue is just the distance CB, right? Oh, and sorry, this right here is alpha, right? And so once we start thinking in terms of cosine and sine and all that stuff, because we identified it from sec and cosec, you think about those specific tools. And so you must have learned by now or must have heard, and if not, here's a quick review, that sine and cosine and tangent has associated to, or at least it's how it was taught to me, sine is so, cosine is Soh Cah, and tangent is Soh Cah Toa. So what the heck is happening? Why, like what, right? What is happening? So is telling you that you can have sine of some angle, right, equal opposite over hypotenuse. That's why so, OH, opposite over hypotenuse. Meanwhile, cosine is going to be Ka, so that means I have cosine theta equaling the adjacent over hypotenuse. And last but not least, you have the Toa tangent, so tangent theta has to equal Toa, so it's opposite over adjacent, okay? So that means that in all of these triangles, you have to be really careful with which one is adjacent, which one is opposite, which one is hypotenuse. And the main thing that most people get confused with is sometimes they put the adjacent as the hypotenuse. Okay? That is the main thing that people sort of mess up, and I need to tell you immediately that the hypotenuse is always the hypotenuse. Okay? The adjacent and the opposite might change relative to which angle you're thinking of, but the hypotenuse is always going to be the hypotenuse. There is no argument there. The hypotenuse will always be the long side. Okay? And you can also understand it as the one that is opposite from the 90 degrees. Okay? The hypotenuse is always the long side. It's always the opposite from the 90 degrees. The adjacent and opposite depends on your angle. What do we mean by this? If this is your angle, right, that means that this is your adjacent. But if this is your angle, then that means that this is your adjacent. See what I mean? So adjacent depends on where you're standing, but the hypotenuse is always going to be the hypotenuse. See, this one will never be adjacent. This one will always be hypotenuse. Okay, so be careful with that. I might as well mention it because I know it can be confusing and etc. And well, there it is. Okay, so back to reality, back to the exercise. Over here, what can we apply? You stare at it for long enough and you realize that you have an opposite and the hypotenuse. So which one has opposite and hypotenuse? Sine. So up here on top, you can apply sine of alpha has to equal my opposite, which is 6, divided by the hypotenuse, which we said was side CB. Okay? Well, down here, you stare at it for long enough and say, okay, so I have the adjacent next to alpha and the hypotenuse. So which one has adjacent and hypotenuse? Cosine. So down here, you can apply that cosine alpha. So Ka, so it's going to be adjacent over hypotenuse. The adjacent is 3 over 4 divided by side AC, right? Now, from here, we still need to finish proving, showing, etc., right? And so why would I do this in the first place? You would do this in the first place because technically L, this distance L, right? The long line has to be, and I should have mentioned this earlier to be honest, that distance L, right, has to be AC plus CB. And here you just created equations that have CB, that have AC. So that's why we're doing this in the first place. If you find AC and you find CB, that will be, and you add them together, that will be the length that you're trying to find, and that will pretty much show that L has to be this. See? So we need to get AC and CB alone, like respectively in each of their scenarios. And so up here, what you can do, right, is that you can multiply by CB on both sides. So that means that you have CB times sine alpha equaling 6. Now, you wanna have CB alone, so you can go ahead and divide by sine alpha to both sides. This goes away with this, and CB has to equal 6 divided by sine alpha. Okay? Now, our show that has sec and has cosec inside of it. So we looked into the formula booklet, we found out what it was, and it's basically just 1 divided by cosine or 1 divided by sine. And so in this case, I have a sine on the bottom, right? So if I, just to make this very, very clear, when you have 6 over sine alpha, it's the same as if you wrote out 6 over 1 times 1 over sine alpha. Okay, it's the same thing. It's like the short version, the long version, it works the same, okay? And so, here you have a 1 over sine alpha. So that right there, ladies and gentlemen, is cosec alpha. And so, boom, will you look at that? CB equals 6 cosec alpha. And so on the one hand, we just found our value for CB, right? And our value for AC, well, we do a very similar approach. We're going to multiply by AC to both sides in order to get it out of the fraction. So you end up with AC cosine alpha equals 3 over 4, right? You divide by cosine alpha in order to get AC alone. A very sort of similar approach, right? And eventually you reach that AC has to equal 3 over 4 times 1 over cosine alpha, okay? Because you're dividing by cosine alpha, it goes in like this, and bada bim, bada boom, this, as we saw earlier, is that. So, this makes it a lot more friendly. AC has to equal 3 over 4 sec alpha, right? Sec alpha. And so if now I apply my formula from earlier, that is basically this long distance has to be what's in green plus what's in blue. Clearly you end up with AC, which is 3 over 4 sec. So you end up with your big L being 3 over 4 sec alpha plus CB, which we said was 6 cosec alpha. Bada bim, bada boom, it is the same thing that they told us to show down here. So ladies and gentlemen, part A is not that tough, but you do need to be aware of what sec and cosec is. And really, you don't have to know it by memory. That is the biggest sort of energy I'd like to transmit to you. You don't have to know it by memory. You don't have to be a math grandmaster or anything crazy like that, but you do need to be someone that knows what's in their formal booklet roughly. Okay, so you should reach the state where you reach sec, where you read cosec, and you say, I know I've seen that before. Let's look it up. I know it's somewhere in there. What's going on? See? So you figure out what's going on. You realize it has a cosine and a sine, and boom, those are already huge hints that, okay, you need to use cosine and sine. So you draw your triangles, and it becomes very evident, right? You do a quick review of what cosine and sine, how it's written. It's Soh Cah Toa, and everything just kind of flows. See? So again, being familiar with the formula booklet is the number one like tip I can try to give anyone that watches my videos. Okay? Anyways, enough blah blah. Let us now move on to part BI. Okay, so part BI is asking you to find basically just the derivative of L in respects to A. And so the derivative of L in respects to A. On the one hand, a quick reminder, if you couldn't do part A, you can move on to part B because this is a fact. Okay, so you can just do the derivative of this immediately if you never did part A. Keep it in mind to claw some points if you're running low on time or you get stuck or you get stuck or whatever. See? Yeah. That being said, what the heck is the derivative of this? And so again, you need to go to your formula booklet because the derivative of sec or cosec or sine or cosine, you can end up like memorizing them, but most of us right now probably don't, and that's perfectly fine. I might as well double check you guys. And so because we're entering the realm of derivatives, right? Because we're entering the realm of derivatives, we are talking about the land of calculus, everyone's favorite. And so page 12, HL, we're part of the cool team now, so we can go to page 12. So page 12, here starts the calculus, and there's a bunch of standard derivatives. See? You actually have cosec in here, which is interesting, right? So we might end up using cosec right there. Let's see what else we have. A bunch of crazy stuff. A bunch of crazy stuff. See? Yeah. Standard derivatives. Derivatives, yeah. So yeah, we're probably just gonna end up using this page right here. And so on the one hand, I can use the derivative from the formula booklet for cosec, right? So I can use that for this part. And oh, I have one for sec as well. See, so I can use that here as well. Let's just do it and see what happens, right? And so for finding the derivative of dl in respects to dA, right? For sec A, we can see that sec, right, is just gonna keep the sec, right? So it keeps it, and you multiply with a tan. Okay, that's it. So you keep the original and you multiply with a tan. So for this first term, okay, which I will be doing in whatever, in pink, right? So for this first term, the 3 over 4 stays because it's, well, multiplying my term, right? We leave sec A, or sec alpha, sorry, because we're following from the formula booklet, and we multiply by tan alpha. That's literally it. See, so this is sec alpha times tangent alpha. And then for the next part, right, for the next part, which I will do in this yellow, actually, no, that yellow looks terrible, in this, whatever, this color, yeah, 6 cosec alpha. So what does cosec do? Cosec, on the one hand, okay, means that you put a negative in front and you multiply by cotangent x. Okay, I know this looks crazy, and I know some of it maybe you don't recognize it, you're not sure what it is, but trust the procedure, trust the formula booklet. This is their derivative for cosec, so we will follow it word by word. So on the one hand, you will end up with a -6. The 6 sticks around, that is not going anywhere, so -6 times cosec alpha, so that stays, following from the formula booklet, right? The cosec stays, and then you multiply it by cotangent of alpha, right? Cotangent alpha. All right, perfect. So there's my derivative. Not that complicated. Go ahead and leave it a little nicer, which would really only be that this plus and negative makes you leave it as negative this. See? So there is my derivative. Not that hard. You just gotta be familiar with the formula booklet. See? Don't be the guy that looks at this derivative and says, damn, I never learned the trigonometry derivatives. Like, I'm screwed. Take a moment, think about it. You know it's in your formula booklet. Find it. Do it. Okay? You can do this mainly just by knowing that it's in here. Okay? So keep that in mind. That is for part BI. See? For part B double I, they tell us that when your derivative equals 0, okay, that's all it's saying. That is all it's saying. When your derivative equals 0, show that, so this is also something you can take as a fact, show that alpha equals arctan 2. So, the first thing I'm going to go over is what the heck is arctan 2, right? Or what the heck is arctan? So, my quick review for that is the following. A lot of times in these exercises of sine, cosine, tangent, etc., for example, imagine you have, I'll make it up, but imagine you have sine theta, okay, equaling 1/2, right? And so this theta is an angle, okay? And if you were to get that angle alone, like if you want to find the angle, well, you need to get theta alone. So what is the opposite of sine? Well, think about it this way. What is the opposite of multiply? It's divide. What's the opposite of adding? It's subtracting. What is the opposite of sine? It's sine inverse. And so multiplying is the inverse of division, adding is the inverse of subtraction. The inverse of sine is literally just sine inverse. And so if you apply sine inverse to both sides, this goes away with this, and you end up with theta equaling sine inverse of 1/2, okay? That is the main idea of why you use inverse. Now, for some reason, a bunch of people wanted to get fancy, and if you face the same exercise, just that you're using tan, so tan theta equals, I don't know, 1/2. Again, I'm just making up the numbers. And you apply the same thing, like, okay, you gotta do tan inverse, and then tan inverse. This goes away with this. Theta equals tan inverse, okay, of 1/2. And for some reason, you can also write this as theta equals arctan 1/2. Really, you can write it like arctan instead of tan inverse. See? So all the arctan is really doing is like, dude, it's a synonym for tan inverse, okay? That is the intuition I'm going to share with you. So arctan is not so spooky, and it's actually a little bit of a hint. You gotta get tans in there. So get tan in there. So that is a big hint. Get tan in there. Eventually you will be using a tan inverse, and it's written as arctan. Okay, that's all that's really happening. That is also why they get alpha alone, because alpha is inside all of these parentheses. So eventually you put every, that's the thing. Because you reach that alpha is arctan 2, which we said was just tan inverse, right? You need to have everything in terms of tan. So everything in terms of tan, and then you do tan inverse and you get alpha alone. And so this right here is actually giving you so much information than what you think. It's telling you all the things I just mentioned. On the one hand, you need to get tans in there because it's arctan. Like, just starting off with that, see? On the other hand, because it's arctan, you will be doing tan inverse. And also, because you're leaving alpha just in terms of arctan, everything needs to be in terms of tan. Or else you would also have a plus sign going around, which you don't. So, you need to do those things, right? Just leave it in terms of tan, figure out what happens, how to do it, etc., right? So we will need a little bit of space. So let me put that maybe up here, right? So let me erase this for a second. So as I said, keep in mind, you need to put everything in terms of tan. And you might be thinking, dude, I have no idea how to put everything in terms of tan. But what you should have an idea of, and if not, you will learn that now, is that for putting stuff in terms of tan, okay, or cosine or sine or etc., you have a bunch of trigonometry properties, okay? And so all of those trigonometry properties can really help you jump from one, like cosine or whatever, to the next, right? And so first things first, our derivative was equal to 3 over 4 sec, I think it was, sec alpha tangent alpha, sec alpha tangent alpha, just give me 1 second to do this, minus 6, I don't know why I put plus up here, but whatever, see, minus 6 cosec alpha, minus 6 cosec alpha, right, minus 6 cosec alpha, times cotangent alpha, times cotangent alpha, right? So this is my derivative, okay? And they tell us that when this equals 0, right, we need to show, that's the thing, when this equals 0, show that alpha equals arctan 2, right? So first we will equal it to 0. That means you end up with 3 over 4, well really, let's make it a little quicker, right? So this equals 0. This whole thing equals 0, right? So when this whole thing equals 0, that means you can do plus this whole thing, just so that everything remains in terms of positive terms, right? So plus this to both sides. This is legal because there's only a negative affecting everything, right? And so this goes away with this. You end up with 3 over 4 sec alpha times tangent alpha equaling 6 cosec alpha, right? Cotangent alpha. See? Now let's first go with what is most friendly. I will actually first go through the 3 over 4 and the 6. See? So technically, if you want to sort of leave this more nicely written, you can first do times 4 to both, right? So that means this goes away with this. You end up with 3 on the left, and on the other side, you end up with 24. And if you divide by 3 now, so this goes away with this, and divide by 3, that means on the right side, you end up with 8, all right? So there I was just playing around with the numbers. You can make this disappear, and eventually you will reach an 8 on this side, okay? Now the next thing we have to really embark upon is that, okay, we end up reaching an arctan, so you need to put everything in terms of tan. How the heck can I do that? And so clearly you need to like sort of get rid of the sec, get rid of the cosec, get rid of the cot, right? Of the cotangent. So on the one hand, we did see earlier, right, that sec was 1 over cosine alpha, see? And this is already a step like forward because we're getting rid of the sec and leaving things in terms of sine, cosine, and tangent. Now, some of you might be wondering, why would I want it in terms of sine, cosine, and tangent and not in terms of sec? Well, because in your formula booklet, you have a bunch of, let me find it. Okay, this is not in calculus, it would be in trigonometry. You have a bunch of identities. So you have a ton of identities going around, right? Trigonometry identities, identity for tan, this or that, etc. And a lot of it has to do with sine and cosine, see? So on the one hand, you can get rid of the sex, you can get rid of the sec, you can get rid of the cosec, put it in terms of cosine and sine, and if everything is in terms of cosine and sine, you can start thinking about applying this. So tan can get written as sine and cosine, so if everything is in terms of sine and cosine, you will be able to reach tangent more easily. Okay, that is the main idea I'm trying to tell you. And the way to sort of realize that is being familiar with the formula booklet. So once you're familiar with the formula booklet, you can have that sort of realization that, because I need everything in terms of tan, I first need everything in terms of sine and cosine. So the sec alpha, we can write it as 1 over cosine, see? So here on the left, you can immediately put tan alpha divided by cosine alpha. Okay, so that is already a little more friendly. On the right side, you end up with 8 times cosec alpha. Now, cosec, we did say was 1 over sine. So that means I end up with 8 times cotangent alpha divided by sine alpha. Okay? Now, for the cotangent, it's a little bit more tricky to try to get rid of that. So the cotangent, let's go and take a second and look over here. Where does cotangent appear? What is going on? You do have a cotangent that appears right there. See? Now you will turn to cosec, and it's a little bit of a longer process. So let's see if there's a little bit of a different approach that we can do. So give me a second. Let me try to remember, right? Okay, so what I would do, thinking about it a little bit more, is that from here you can leave it as tangent alpha divided by cosine alpha equals 8 cotangent, okay, divided by sine alpha. And so from here, you can now cross multiply. So that means that you end up with 8 cotangent alpha times cosine alpha, right? Equaling tangent alpha times sine alpha, right? Now, the the identity for tan is sine following this. See, it's sine divided by cosine. So you want sine on top, cosine on the bottom. So that means you can do divide by cosine, right? And eventually you end up with, this goes away with this, 8 cotangent of alpha has to equal, this whole thing is going to turn into tangent, right? So that means that on the right side you end up with tangent twice of alpha. Ah, interesting. And so from here, the cotangent, okay, which is something that I didn't mention like thoroughly before, but the cotangent, okay, cotangent is 1 over tangent, literally. Okay, so much how you have um, sec or cosec for 1 over cosine, 1 over sine, you also have cotangent being 1 over tangent, literally. Okay, so that is not in your formal booklet, or not that I've seen. This is the kind of thing you have to know. So much how you have sec for 1 over cosine or cosec for 1 over sine, you do have cotangent for 1 over tangent. So that being said, I come back over here, and the cot, I can just write it as 8 divided by tangent, right? And now we're almost done. Everything is in terms of alpha. It looks much more friendly. So from here, you can multiply by tan to both sides. Multiply and multiply. This goes away with this. 8 equals tangent cubed, parentheses alpha. And so from here, in order to get rid of the cubed, you can go ahead and do square root with base 3, right? So that means that on the right side, or actually, you would end up with just 1 tan, right? So tan alpha is going to equal 2. It equals 2 because basically right here, you're asking this thing, which number multiplied by itself 3 times gives you 8, which would be 2. 2 times 2 times 2 gives you 8. And so from here, because you want to get alpha alone, because eventually you want it to reach the alpha equaling something, right? You can go ahead and do tan inverse. So you do tan inverse to both sides, tan inverse, tan inverse. You end up with alpha being equal to tan inverse, right, of 2. But I mentioned a long, long time ago that tan inverse is basically the same as arctan. And so this alpha equals tan inverse 2 is the same as saying alpha equals arctan 2. So, ladies and gentlemen, that is how you would show that alpha equals arctan 2. So that was a lot of points. That was 5 points in total between both parts. There's a lot of stuff you have to know, and more than anything, to my judgment, it's being familiar with the formal booklet. So, that is how you do part B, part double I. Alright, guys, and now for part C, part I, we need to find this. Now this, okay, just so that we're all on the same page, this is really just asking for the derivative, okay? The derivative twice, alright? And so if from part BI, we did the derivative, this is basically just derivative in respects to alpha once. So if this is the derivative once, here we need to do the derivative twice, or you can also think about it as like you're doing it again, okay? And so this is just a very fancy way to say that in respects to this function, you're doing the derivative twice, this time in respects to alpha, and basically again, see? Because in theory, you could do the derivative again, but in respects to a different variable. But what we're always going to face, at least us in this class, all right, or at this math level, as far as I'm concerned, is the same variable again. So you are doing the derivative in respects to L, sorry, in the function L in respects to alpha twice, okay? So from parts BI, I have written up here the first derivative, and now we need to do the derivative of this again. And of course, a couple things arise from here, and the main thing that the IB is trying to test us on from here is what we call the product rule. Now there's a couple different derivative rules that we need to be aware of, and there's three of them. Okay, the one we're going to be using is product rule, but you also have the chain rule. Okay, and the other one that you can also face is what we call the quotient rule. Okay, so I really need to go over these for just a quick second. Now, before we look at the formula booklet and get incredibly anxious because the derivatives look absolutely crazy, let's first understand intuitively which one is which, when to use which. So let's go with the easier ones to understand first. Product rule, following its name, has to do with multiplying. Okay, so whenever you have your variable being multiplied with itself in any way, you should be considering the product rule. Now, I'm not talking about doing the derivative of x times x and ending up with x squared. No, ladies and gentlemen, I'm talking about the product rule when you have something like sine x, so x is on one side, times cosine x. Okay, here you would consider the product rule because you have two x's multiplying each other and they're sort of like separated by something. See, this x squared is not separated by anything. In fact, over here you would actually apply the exponent, just derivative of an exponent. See, derivative of an exponent. It's a little bit different, see? So product rule is something you consider when you have something like sine x times cosine x. Or you have, I don't know, like log x times x. Actually, that would also work as a product rule, see? So be wary of that. You should be thinking of product rule when you have your x's or the variable you're trying to do the derivative of multiplying each other. Okay, so keep it in mind. That is the intuition that I need you to go forth with. For the quotient rule, it's awfully similar, just that you now have dividing. Okay, so instead of having log x times x, it would be something like log x divided by x. Okay, here you would apply the quotient rule. Okay, and last but not least, the chain rule is perhaps the weirdest one, but intuitively it's easy to follow. It's basically just when you have one inside another, okay? So, for example, here I put the example of the sine and cosine. Well, an example for chain rule could be like you have sine of cosine x. And so this x, basically, right, this x is within two different functions. See, it's the same as if you put log and then sine x. Okay, so you have two sort of like functions that are chained together. Okay, you have first the log, then the sine. Okay, here you have first the sine, then the cosine, and notice how x is like deep in there. Okay, so you first gotta go through sine, then through cosine. That's the intuition of the chain rule. It is one inside of another sort of function or whatever. See? Now, the product rule has to do with multiplying. See? And the product rule, once we look at the formula booklet, you will realize that it is pretty crazy. Okay? Unless you like study this a lot, you're probably looking at this saying, I'm screwed. Okay? You're probably looking at this thinking like, this is insane. I should not have signed up for this, but it's too late. Gotta do what you gotta do, you know? So, anyways, you're probably looking at this. Maybe you have your test in 30 minutes or 30 days. Nobody knows. But you gotta learn this. Okay, there's no other way out. See? And one of the things that I love but also dislike about the formula booklet is that although it does have all the formulas, a lot of times it's not that intuitive. See? And so imagine just for a second that the product rule is rewritten. See? And so the product rule, what they tell you is that it's the first one. I mean, the product rule, you have your two terms, right? Which is the same as if I wrote here sine x times cosine x. See? So u would be sine x and v would be cosine x. Okay? So, how the product rule really works is that first you take first first you take the first one. So, initially you take the first one and you multiply it by the second one in its derivative version, plus the first one in its derivative version times the second one in its normal version. So this like for me at least, is much easier to follow just like visually. So the first one, like sort of normal, times the second one with the derivative, plus the first one with the derivative times the second one like normal, see, or unchanged, however you want to think about it. And so really this formula that I erased, that's what it's telling you, okay? This symbol that I'm putting here for like its derivative version is that thing right there. Oops. It's, it's that thing right there. Okay, I'm like highlighting everything, damn it. So it's, here we go. It's that thing right there. While over here, the derivative of that guy, ¿cierto? It's that guy right there, okay? So it's all the same at the end of the day, but for me, it's much more intuitive if I think about it like, so the first one normal times the second one with a derivative plus the first one with a derivative times the second one normal or unchanged, okay? And if you really sort of look at it that way, even the quotient rule gets a little bit more friendly, see? And so the quotient rule, I mean, we're not going to use it today, but I do want to like help you understand the formula a little bit better. So just real quick, what you end up with is really, okay, so V, notice V is the denominator, see? So V is denominator, while U is numerator. So really, the quotient rule is telling you that you do the denominator times the numerator being derivatized minus the numerator times the denominator derivatized divided by the denominator squared. So really your derivatives are with the numerator here and the denominator there. So for me, that is a lot easier to follow. I don't know. I thought I would share that sort of tip that yes, the formula booklet is amazing because it has everything, but you do have to understand it in your own way. This is how I understand it. Maybe it helps. Okay? Anyways, enough blah blah. Let's get back to reality. So over here, clearly we have the product rule. Now, as I established earlier, I like to think about it as the first one unchanged times the second one with the derivative plus blah 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 blah. Okay? Yeah, cool. So let's follow the formula like piece by piece. See? So first, and careful with this, first you will do um the product rule on this term, and then you will do the product rule on that term. Okay, so it's two different operations. Let's do the product rule of this first one. So the product rule of this first one means that I have 3 over 4, right? And sec alpha, okay, will be like my u, yeah? So just to be very, very careful, because I know this can get really wild, this is going to be like your u, okay? So this is going to be like your u, and this is going to be like your v. Okay, so just that none of us get lost, this is what I'm following in my head, okay? So the product rule here means that the first one remains unchanged, see? So I end up with sec alpha times the second one in its derivative version. And so the second one in its derivative version, well, I had to do the derivative of tan. Now, nobody knows, at least, yeah, I would say that nobody knows, let's be honest. So nobody knows the derivative of tan. So you open up your formula booklet, blah, 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 find the derivative of tan. Here it is, ladies and gentlemen. So the derivative of tan is just sec squared. So that means I end up with sec squared alpha. All right, so there I did, technically I just did this part here, see? I still need to do this part over there. And so for this part over there, it's the first one with the derivative, see? Oh, and also, sorry, you put a plus in between, see? So you do plus, again the 3 over 4, don't forget it, plus the 3 over 4. The first one being derivatized, so the sec alpha, right, with the derivative. So the sec alpha, what is the derivative of sec? Nobody knows. Check your formula booklet. So the derivative of sec is right there. Look at that, how friendly. So it's really just you multiply by 10. I mean, that's it. You multiply by 10. See? And I know you might be thinking, "Ugh, this is getting crazy. This is getting nasty. I am ending up with a lot of stuff on my piece of paper." And I'm going to say, yes, you're right. You signed up to AAHL. You got to deal with it. Okay? But trust the process, especially for these double derivative problems. And whenever you have a product rule in between, you will end up with a massive answer. Okay, so that's normal. Get used to it. Don't worry. So this is the derivative of the first one. See? Now we have to multiply it by the second one unchanged, following this here. See? So now the second one unchanged times v. So v we said was just tan, so times tan alpha. Okay, that's what's happening right now. That right there is the product rule of the first one. See, and just so that we're all on the same page here, here's my u, here's my v with a derivative, here is my u with a derivative, and here's my v. Okay, that is what just happened. Now, I gotta do that thing again, but now with this guy. Okay, so of course I'm gonna run out of space, so I'm just gonna put it down here. See, now we're gonna call this the u and this the v. Okay, so once again we have to start with minus 6 and following this formula over here. So first it's the u times the v with derivative. So the u is going to be unchanged, so I just write down cosec alpha, it stays normal, times the v with derivative. So derivative of cotangent, do you know it? I don't. So let's go over here. Here is cotangent. Let me double check. Yes, so derivative of cotangent is just going to be, wow, look at that. That's kind of wild. So you end up with negative cosec squared. All right, sure. I mean, I didn't make that up. So negative cosec squared alpha. Trust the process. It's gotta be what it is, right? So, yeah. So here I would have the u, and here I would have the v. See? Now you gotta do the plus, correct? Now you gotta do the plus. And following over here, now it's the first one with derivative times the second one unchanged. So the first one with derivative is derivative of cosec. Do you know it? No, you don't. Go to the formula booklet. Cosec is right there. So cosec ends up as this crazy thing. So it's the same cosec but with a negative, and you multiply by cotangent. All right. I mean, what the heck? See? So I put the plus, but I still start with the negative 6. So it's negative 6 times negative 6 cosec alpha times cotangent alpha. Yeah, so this right here that I just put is derivative of the first one. See? Times the second one unchanged. And so the second one unchanged is just going to be cotangent. So there is the second one unchanged. Okay? So I know that was kind of confusing because it is confusing. See, so if you got lost at some point, like make sure you double check, you review, etc. Product rule is confusing you guys. See, so practice it a couple times. For me, it helped a lot to understand that first I changed this, the second one not, then the second one gets changed, but the first one not. See, stuff like that. Just practicing it a lot, seeing a lot of examples, and doing this a lot of times, so you really understand the logic behind it is key. Okay, understanding why it works the way it works, or the pattern that is like behind it is huge. Okay, that's the best thing you can do for yourself. See? Now, obviously it's the AB, so you gotta leave your final answer at least in a nicer way. Or at the very least, it's convenient to like group it together for down the road. See? So, for this guy here, what you end up with is 3 over 4. You can find the sec. You combine the sec. So it's 3 over 4 sec to the power of 3 alpha. For this next term over here, right? You can combine the tangents. So you end up with plus 3 over 4 sec alpha times tangent twice, or tangent squared. See? Next, we can move on to this one here. So boom, you can do that one. Clearly, you have 3 cosecs going around. You do have 2 negatives though, so careful with that. You do end up with plus 6 cosec cubed. And this last term, I'm probably going to run out of space, but this last term is right there. Notice how you have a plus and a minus, so it's plus minus. So it ends up being negative. See, so here now you do minus 6. Okay, I'm definitely going to run out of space there. See, it's fine. No harm done. Minus 6 cosec alpha and cotangent twice. See? So there is my final answer. Here is the second derivative of my function. And let me just show you the mark scheme just so you believe me, believe this guy on the internet. You end up with a pretty crazy long answer, and it's right over here. See, so as you can see, you end up with the 3 over 4 sec tangent twice. So here's the sec tangent twice. The sec 3 times, the sec 3 times. Then over here it's 6 cosec cotangent twice, 6 cosec cotangent twice, and last but not least, the cosec 3 times. See? Now, small mistake that I've committed, which we will find together because it can happen to anyone. I'm leaving it in the video because learning moments are all around, especially when I make a mistake. Here's a negative, and here is a positive. So where did I mess up? What happened? This can happen to anyone. So clearly, I must have messed up somewhere on the derivative when I was doing the derivative of cosec. See? So when I was derivatizing cosec, what the heck happened? So when I derivatized cosec over here, well, let's take a moment to understand what happened. So the derivative of cosec, as you can see, and now I immediately see my mistake. So the derivative of cosec is that this cosec ends up with a negative in front. See? Now, I kind of got confused because there's already a negative here. So what I should have done is that I do plus minus 6, and then here I needed a negative cosec. See, so following the formula, it would have been like that, technically. And so that means I have the plus, the negative, 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 plus. This should have been a plus. See? So small detail, I am leaving it on the video because it can happen to anyone. And you know, I mean, what better learning moment than you messing up? See? That's life. We only get better with time. Mistakes happen to anyone. Take it easy. See? So anyways, small mistake, there's my plus. Bada bing, bada boom. See? So, wow, that was crazy. But it is worth 7 points. So fair is fair, right? Then they tell us that when alpha equals arctan 2, show that this equals that. Now this next part, you guys, this is very big brain. Like, I'm just going to tell you right away, it's very big brain. There's a lot of stuff you need to understand. There's a lot of context you really need to swallow for this to really make sense. Okay, so let's try to go piece by piece as safely as possible. So right now, right now you have sec, you have tan, you have cosec, and cotangent. So we have sec, right? We have tangent, right? We have sec, we have tangent, we have cosec, and we have cotangent. We have cosec, and we have cotangent. And so apparently from this, okay, because they tell us that alpha equals arctan 2, I should reach an actual value. So why am I setting it up this way? Notice, my current derivative has a sec, has a tan, has a cosec, has a cotangent, and all of these, you guys, disappear. Like, they get consumed, they get turned into an actual number, and if you add up all those actual numbers, you end up with this right here. How do I know you end up with this right here? Because it says show that. So you have to reach that. It's a fact. So how the heck from here do you somehow get rid of all of this, turn it into numbers, and end up with an actual value? Okay, that is a massive sort of concept jump we have to go for, and let's try. See, so first things first. Why is it so useful that alpha equals arctan 2? See, I did go over that a little bit before earlier in part B, part double I, but basically, how do you reach an arctan? Well, arctan, you guys, so arctan is the same as if you were saying tan inverse, okay? So that means that that technically right here, see, at least for me it's easier to understand. So right here you have tan inverse, right? So that means the step before this meant that you had tan on the left side. So before this, right, that means you had tan here equals 2. So really, um, knowing that you have that alpha equals arctan 2, right, which is the same as just tan inverse, you can apply like tan on both sides or something like that. I'm sure it works like that because it's an inverse, see? And you end up like figuring out or whatever that tan alpha equals 2. Okay, that's the big sort of thing that's happening. See, so tan alpha equals 2. And so this actually helps you because now, so all the tan alphas have to equal 2. Now, how in the heavens is that ever going to help me out for sec, cosec, and cotangent? Okay, that is the big challenge that is happening now. And so, what is the formula of sec, cosec, cotangent? The formula of sec, for example, if you go to the formula booklet, because once again, the formula booklet got like everything. So go to topic 3, not topic 5. It's not a derivative anymore. Now we're talking about um, trigonometry and stuff like that. See? So for HL, because we're big boys now, big team, yeah, we are full grown adults doing big important things called IB Math HL. See? Um, Notice, so sec is just 1 over cosine. See, so let's go ahead and write that. So sec alpha is just 1 over cosine alpha. See, we're not sure how it might help yet, but let's just write it down. See, cosec on the other hand, so cosec is just 1 over sine. Yeah, cool. So this is 1 over sine alpha. Well, cotangent, I'm not sure if cotangent is here. I think it's not. But cotangent is very similar to the inverse. It's just telling you 1 over tangent alpha. See? So cotangent alpha is just 1 over tan alpha. See? All right. So why would this be useful? It's useful because in trigonometry, and this is huge, you guys. So I'm actually going to write it down over here. See? So in trigonometry, you do not care. This is very important. You do not care about the lengths of your triangles. You only care about the angles and this is a hugely important word and concept, proportions. And so, because you don't care about the lengths of your triangles and you only care about the angles and the proportions, this is actually a massive amount of information for understanding the proportions of this exercise. Bear with me for a moment. So, tangent, you guys, we know comes from Soh Cah Toa. So, Soh Cah Toa, as I mentioned earlier, for sine, right? So, for sine, the Soh is going to be opposite over hypotenuse. So, this is for sine. See? I'll just, whatever. So, this is sine, right? For cosine and for tangent. So, for sine, you have opposite over hypotenuse. For cosine, you have adjacent over hypotenuse. And for tangent, you have opposite over adjacent. So, what's the big deal here? Basically, because alpha, because alpha, see, tangent equals 2, you can basically say, right, you can basically say that opposite over adjacent equals 2. Now, Because you do not care about lengths of triangles and you only care about the angles and proportions, from here you can think about, okay, so opposite divided by adjacent has to equal 2, so the most obvious explanation is that opposite equals 2 and adjacent equals 1. And there might be a part of you sort of like protesting me saying, can't you say that opposite equals 4 and adjacent equals 2 and you would get the same answer? And on the one hand, I would say yes, and you can actually solve it like this, and you will get the right answer, I promise you, only because you do not care about the lengths of the triangles, only that the proportions and angles are appropriate. And so yes, you can solve it thinking about it like this, but might as well pick the friendlier version, right? So opposite is 2, adjacent is 1. As long as it makes sense and you follow through with these proportions, okay, you will be okay. So, you are now establishing that the opposite equals 2 and the adjacent equals 1. Now, if I were to try to plug it in for Soh Cah Toa, right, I'm not quite there yet because I still need to figure out what hypotenuse is before actually using any of these formulas. And why would you use these formulas? Because it would help you define sine and cosine. And if you define sine and cosine, suddenly, boom, you unlock this. Boom, you unlock this. And boom, you already have that, actually. So, that is why we're doing what we're doing. See? Figuring out sine and cosine helps you figure out sec and cosec. And how can you do this? Well, because tan equals 2, that means you have a proportion of opposite and adjacent equal to 2. And since you do not care about lengths of triangles in trigonometry, only about angles and proportions, you just say that the opposite equals 2, adjacent equals 1. How do you get the hypotenuse from here? Well, technically, right now you have a triangle that you know has alpha here. See? And you know that in respect to alpha, you have an opposite of 2 and an adjacent of 1. So what's the hypotenuse? Will you look at that? Will you look at that? So Pythagoras theorem, a squared plus b squared equals c squared. 1 squared plus 2 squared equals hypotenuse squared. 1 plus 4, cierto? 1 plus 4, I'll just write it out. Okay, so 1 plus 4. So hypotenuse squared equals 5. Hypotenuse, ladies and gentlemen, equals square root of 5. And so, boom, hypotenuse equals square root of 5. It's gotta work. It's gotta work. We are definitely onto something. Da, 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 da. It's kind of exciting, I'm not gonna lie. So, this means that for sine, okay, this means that for sine, let me make a little bit of space, okay? So, right now, the proportions that make this make sense is that opposite is 2, adjacent is 1, and hypotenuse equals square root of 5. And so if you go ahead and plug in, that means that sine alpha equals opposite over hypotenuse. See? So it means that sine alpha is 2 over square root 5. That also tells you that cosine is adjacent over hypotenuse. So adjacent over hypotenuse would be adjacent over hypotenuse. It would be 1 over square root 5. See? And so now you can plug in up here knowing that information. So following this line, you have 1 over cosine alpha. So you have 1 over, well, cosine alpha is 1 over 1 over square root 5. See? I'll explain how to solve that in a second. Tangent alpha equals 2. Cosec is 1 over sine alpha, cierto? Sine alpha is 2 over square root 5. So here you have 1 over 2 over square root 5. See? And this last one is just 1 over tan alpha. Well, tan alpha is more straightforward. Tan alpha just equals 2, so this is the same as 1 over 2. See? So this one is already sort of like completed. Cotangent, right, is going to be 1 half. See? So this is for cotangent. That one is already done. Tangent alpha is also already done. Now we need to finish clearing up these weird sort of fractions. So these fractions, you guys, there's a couple of different ways to think about it, and what I suggest, or my approach really, is that you want to have two fractions on top of each other. See? For me, it's easier to think about it. So if up top you have a 1, That means up top technically it's just 1 over 1 divided by 1 over square root 5. See? Well, here down here you have 1 over 1 divided by 2 over square root 5. Now from here, what I like to do is just that when you reach this sort of scenario of two fractions on top of each other, resulting in one big sort of fraction here, ¿cierto? The way you solve it is, well, technically, if you have a over b divided by c over d, it's the same as saying a over b divided by c over d, see? And because you are dividing fractions like this, you gotta do the reciprocal for multiplying, see? So this, you must have learned at some point, turns into this. So you flip the c and d, right? So that is one way you can sort of think about it and reach that. The other way you can think about it, which is what I love to do, is you do the edges multiplying each other and the middle ones multiplying each other. Okay? So basically here you end up with 1 times square root 5 divided by 1 by 1. By 1 over 1, sorry. See? So just square root 5 is going to be sec alpha. See? So sec alpha is going to be 1 over square root 5. See? Meanwhile, the cosec, we have 1 times the square root of 5, so just square root of 5, divided by 2. That's my final answer. So cosec is now going to be square root of 5 divided by 2. And so now you can plug everything in, and notice there was a lot of information hidden in this arctan. See? The main thing, I mean, really, I feel like this is a kind of exercise that you face one and you're prepared for it forever. This is just the kind of thing you have to know. See? So in trigonometry, you do not care about lengths of triangles, only about the proportions. So if they tell you that you have alpha equals arctan 2, that means you have tangent of alpha equals 2. And that gives you so many different proportions over here. It lets you get the hypotenuse, etc., etc. And you can just sort of plug everything in, right? So be wary of that. Be conscious of that. See? Yeah. Damn. Okay, that was a lot of stuff. So over here, let me just write somewhere, I guess. Let me just write that sec. Let me use a different color. See? So we know that sec alpha is, just so that I'm not scrolling so much. So sec alpha is square root 5. Square root 5. Tangent alpha equals 2. Then I think it was cosec. Yeah, so cosec is going to be square root 5 divided by 2. So cosec is going to be square root 5 divided by 2. And last but not least, you have over here that cotangent is just 1/2. Yeah. Cotangent is just 1/2. Okay, cool. So if you go ahead and plug in all of that stuff, on the one hand, you end up with 3 over 4 times this sec cubed. See, so sec, we said was square root 5, so you end up with square root 5 3 times. We'll see what happens there. See? Plus 3 over 4 times sec, right, sec alpha, which we said was square root 5, times this tangent twice. So times just 2 squared. That's a little bit more friendly. Plus 6 times cosec 3 times. So cosec cubed, basically. Plus 6. So there I just did this. See? Now I'm doing 6 times cosec once. So cosec is square root of 5 divided by 2. Times cotangent squared. So cotangent is 1/2, right? 1/2 squared because of this squared. See? So just follow the procedure. Take it easy. I know it's a very long line of math. But hey, this is worth 7 points for a reason. See? So keep going. We finally got rid of all the sec, tangent, cosec, and cotangents, and blah, blah, blah. See, right? So now we can really try to solve it and see what the heck happens. So for this first term, you can end up with 3 over 4 times, think about it this way. So if you have square root 5 3 times, that means you can do it twice. See? So you can do square root 5 times square root. Actually, just you can write it out, ¿cierto? And you know that this has to be, this is square root 25, right? So this is square root 25 times square root 5. So really you end up with 5 square root 5, right? So you end up with times 5 square root 5, correct? Plus 3 over 4 times 4 times square root 5, 4 because of this guy, see? Plus, and I'm actually going to go down here because I'm running out of space, sorry guys, 6 times that whole thing cubed. So really, this whole thing cubed is square root 5 divided by 2 times square root 5 divided by 2 times square root 5 divided by 2. So on the one hand, you will end up with an 8 on the bottom, and up top, the same as here, you end up with 5 square root 5. So here it's 5 square root 5 divided by 8. Yeah, so 5 square root 5. And then this last term is going to be plus 6. It's just square root 5 divided by 2 times 1 half times 1 half. So it's going to be 8 on the bottom. So you end up with square root 5 divided by 8. So square root 5 divided by 8. Okay, this looks kind of crazy. I'm not going to lie. But we're not done with multiplying and everything yet. See? So let's keep going and just see what happens. Okay? So on the one hand, this first term, right, you end up with 3 times 5 up top. So it ends up being 15 square root 5 divided by 4, right? Now, especially when it starts to get kind of weird or you're not sure how you should be solving, what's the smartest way, well, what do you need to reach? So you need to reach 45 divided by 4 times square root 5. So you're not going to be getting rid of all the square root 5s, which is actually like a good thing to know. And also notice the denominator has to be 4. So let's focus on leaving the denominator on 4 and everything should start to flow. So here's for this first term. Now we do this second term. We have 3 times 4, correct? So you end up with 12 square root 5 divided by 4 plus, now this term here, ¿cierto? So it's 6 times 5, right? So that gives me 30 square root 5 divided by 8 plus, this one is just 6 square root 5 divided by 8. See? Now, as I said, you do want to leave your denominator as 4. That's probably going to make everything a lot more friendly. So on the one hand, you can immediately combine these two guys. So these two guys will turn into 27 square root 5, because 15 plus 12, ¿cierto? Divided by 4. This next term, if you simplify it a little bit, you actually end up with, you can divide by 2 on the top and bottom, see? So 30 divided by 2 gives you that 15. 8 divided by 2 gives you that 4, which is what we're going for. And here you divide by 2 again in order to get a 4. See, so you do 3 square root 5 divided by 4, right? Now you combine everything. So this 27 plus this 3 gives you 30, plus 15 gives you 45. 45 divided by 4 times square root 5. Ladies and gentlemen, that exercise was crazy. I'll be honest. Part C qualifies as illegal in many countries, I'll be honest. Okay? Alright, you guys. That is for part C, part double I. Alright, you guys. So now we will go ahead and do parts DI and part D double I. And so for part DI, we have that we need to hence, this is an important word, so hence, so given everything you just found, hence justify that L is a buzzword minimum when we have that alpha equals arctan 2. So this has a lot to do with interpreting how derivatives work, how the double derivative works, and stuff like that. And so let me do a quick 101 in regards to that. For example, with a quadratic, okay? Let's imagine you have a quadratic that goes like this, okay? When you do the derivative, okay, so when you do the first derivative, yeah, and you equal it to 0, what you're actually doing is asking the function when is the slope equal to 0. Now, why would it be relevant to find where the slope is equal to 0? Well, in this diagram that I just drew here, where's the slope 0? And so over here, it's growing by like a lot, right? And so this slope, I would call it like, I don't know, 4. See? Over here, just a little bit more over to the right, correct? A little bit more over to the right, you have a slope that it's a little bit less now, right? So it's growing at a less of an increased speed or whatever. So here it's growing at, let's say 3. If the other one's 4, this one's 3. And if you keep going with this idea, okay, over there it would be, I don't know, I'll make it up. Like now it's like 1, okay? Well, where is it a slope of 0? Da da da. Let me use this color here. Boom. Right there. You have a slope of 0. And so the reason that you want to equal your first derivative to 0 is because it helps you find where in your function, okay, you have a slope equal to 0. So basically, when you do this move right there, okay, you're finding the x value. Okay, you find the x value that gives you when the slope is 0. Okay, that is why on part b double I, when you equaled the derivative to 0, okay, this is basically what you're doing, see? So you equal your derivative to 0, and you find out that the x value that makes it have a slope of 0 is alpha equals arctan 2. So in this exercise, when alpha equals arctan 2, that is where you have your optimal, see? Your minimum or maximum. And so there's the next question. How do you know if this is a minimum or a maximum? Because technically, you have a slope of 0 when it's a maximum like this, but you also have a slope of 0 when it's a minimum like that. And so how the heck do you confirm or find out whether it's a maximum or a minimum? And so here's the next piece of information that you will be learning for today. We know that we first established that if the first derivative is equal to 0, you will be finding the x values where you have optimums, right? Like a max or a minimum. It's optimization, see? For this one on the left, which I will be doing in green, okay, so for this one on the left, you use the second derivative to find out, okay? You use the second derivative to find out if you have a maximum or a minimum. And so the second derivative in this case is going to be negative. And so think about it this way. The second derivative, okay, the second derivative is telling you, how do I put it? Like, whether your rate of change or slope is getting more positive or more negative. So the second derivative is telling you whether your rate of change or slope is getting more positive or more negative, okay? So in this case right here, you would have a second derivative that is negative, okay? Their second derivative would be negative because clearly one slope over is like one x value over, you suddenly end up with a negative slope. And so that is why the second derivative for a maximum is negative. So for a maximum, right, first you're going to have a derivative equal to 0 for that maximum, and the second derivative has to be negative. All right. Following the same idea for a minimum, which is what we're about to find out, you also have the first derivative equal to 0, and the second derivative, you guessed it, has to be positive because one, now I'm going to do it in dark green, ¿cierto? Because one x value over, for example, right over here, see? Right there, you have a slope that is positive. So, okay, that makes sense. The second derivative for the minimum, okay, has to be positive. All right. So once again, the biggest thing I can sort of teach you or explain is that the second derivative is telling you whether your rate of change, in other words, the slope, is getting more positive or more negative. So once you reach the maximum, okay, once you reach the maximum, from here to the right, you end up with a bunch of negative slopes, right? So that is why the second derivative has to be negative. While for the minimum, once you reach the minimum right here, 1 unit to the right already has a positive slope. So that is why the second derivative has to be positive. All right, so now once we understood that idea, we can fully jump onto part DI. Here we need to justify that L is a minimum when alpha equals arctan 2. So we already discovered from part B double I that when alpha equals arctan 2, you have a max or min. Okay, because you equaled your first derivative to 0, you found out that it was a max or min. You found out that it was thing, like a point of optimization. Okay, there's a lot of different ways that I can sort of try to explain this. Optimization, you can think about it as a vertex. You can think about it as a changing point. So for example, if your function goes something like this, right? So your function goes something like this. Well, you found the changing point. You just got to find out if it's a max or min. Maybe you have a function that goes like that. You found all of these. Are each of these a max or min? Okay, that's the kind of thing we have to discover. So, point is, you know that at alpha equals arctan 2, you have a max or a min. The big question now is whether it's a minimum or a maximum. Here they actually give you the hint, yo, it's a minimum, right? But justify it. So how do you justify it? And so the way to justify it is that remembering that this guy on the internet told you that when you have a minimum, the second derivative has to be positive, because when the second derivative is positive, that means your slope is increasing, right? And so if your slope is increasing 1 unit over, that means it has to be a minimum, because boom, it's starting to go back up. See? All right, that makes a lot of sense. And so all you really have to do for part DI is actually using this part that says show that. You can just say that the second derivative, okay, this is the same as the second derivative, right? The second derivative is 45 divided by 4 square root 5, which you know for a fact is greater than 0. And so that would be your justification for part DI. Yes, it is that simple, but you do have to know this whole interpretation thing. See? So for interpreting minimums and maximums, make sure you write this down somewhere. Okay? Personally, I love this diagram here along with this written next to it. See? Easier to remember, whatever floats your boat. That is my approach. Okay? That being said, we can now keep moving on to part C double I. And so part C double I now asks us to determine this minimum value of L, right? Now, let's go piece by piece, see? So, there's been a lot of stuff happening here. So on the one hand, we started with f of x, okay? Then we had the first derivative, and then we had the second derivative, see? So let's really try to organize what means what in this case, see? So the first derivative, the buzzword we will be thinking of is that it's for slope, okay? The second derivative, the buzzword that we will be thinking of is like figuring out if it's a max or min, okay? That's pretty much why you would use the double derivative, okay? And the original one, of course, is just for finding like xy coordinates. See? Technically all of these have a xy associated to it, but you know what I mean when I say xy coordinates, like actual points that go in your graph, whatever. See? So this is actually for finding your x and y's. See? So the minimum value of L, well, for your minimum value of L, my function up here is L equals that whole thing. See? So really what you have is that you have a function of L in respects to some alpha or angle that you're plugging in. See? So when your angle equals arctan 2, what is this length? And when alpha equals arctan 2, you're going for a minimum. So basically, plug in alpha equals arctan 2 in order to find the minimum value for L over here, right? Now, as we saw in part CI and double I and all that stuff, we did establish that having an alpha equals arctan 2 gives you a bunch of information. So, just a quick recap, all right? When alpha equals arctan 2, it's the same as saying that tangent alpha equals 2, right? It's the same, right? Tomato, tomato, potato, potato. So, when you have that tan alpha equals 2, and you recall for a second that tan is for Toa, right? So opposite over adjacent, you can immediately establish, well, what's the most friendly version of tangent alpha equals 2? You will quickly conclude that the opposite equals 2, the adjacent equals 1, and the hypotenuse equals 5. Just for a quick reminder, or anyone that is skipping over to this part, basically what you're saying is that this is angle alpha, your opposite has to be 2, your adjacent has to be 1, and so for the hypotenuse, what you can do is 1 squared plus 2 squared equals hypotenuse squared, right? And that is how we find that hypotenuse has to be square root of 5. And you might be thinking, okay, how do you find that the opposite is 2, the adjacent is 1? Couldn't you also say that the opposite is 4 and the adjacent is 2? Wouldn't it also work? And I would say yes, it would also work. But all that really matters in trigonometry is the proportions between your sides and your angles, not the actual distances, only the proportions. So pick the friendliest one. When they tell you that tan alpha equals 2, just pick opposite to adjacent 1. Why is it the friendliest? Because you have a 1 for adjacent. That's pretty much it. See? Enough blah blah. So from here, you can now sort of start plugging everything in. See? So on the one hand, because we need to put alpha, right? Because we need to apply the alpha equals arctan 2 into this equation down here, right? For finding my minimum value of L. Well, here you have sec alpha and cosec alpha. And from the formula booklet, you can leave this a little bit more friendly. So you can leave it a little bit more friendly by saying that sec alpha is just 1 over cosine alpha plus 6 times cosec alpha, which is simply 1 over sine alpha. See? Now, you know from some point in your life that sine theta is the same as so, ¿cierto? So so is going to be opposite over hypotenuse, and you also know that so cosine, okay, is the same as ka. So that's going to be adjacent over hypotenuse, okay? So now if you plug that in, you end up with 3 over 4 times 1 over 1 divided by cosine alpha. So cosine alpha is going to be just adjacent over hypotenuse plus 6 times 1 over 1 to make it a big fraction divided by sine alpha. Sine we said was opposite over hypotenuse. See? So now suddenly becomes a lot more friendly. For finding this minimum sort of value, all you really have to do is well, you're like plugging in the fact that alpha equals arctan 2. See? And so what you end up with is 3 over 4 times 1 over 1 divided by adjacent over hypotenuse. So adjacent is 1, hypotenuse was square root of 5. Plus 6 times 1 over 1 divided by opposite over hypotenuse. So opposite we said was 2, hypotenuse square root 5. So 2 divided by square root 5. Now I like putting it in big fractions because you can do this sort of visual trick. I just really like visual approaches. So it's this times this, right? So you're going to end up with this times this gives you square root of 5 divided by 1 times 1. So just 1 plus 6 over 1 times, well, this times this gives you square root 5. And this other one gives you 2. See? So now, because it's just fractions multiplying, you do it straight across. So 3 times square root 5, it's just going to give you 3 square root 5 divided by 4 times 1. So just 4. Plus, you do the same idea over here. So this times this is going to give you 6 square root 5 divided by 1 times 2. So quite simply 2. Now you have fractions here, so you want to make sure that you can combine them as much as you can. Because you are adding fractions, you need the denominators to be the same. So what you end up with is 3 square root 5 divided by 4 plus, here you multiply by 2 on the top and on the bottom, so that you get that times 4, see, on the bottom. So you end up with 12 square root 5 divided by 4. You add all of this, you end up with 15 square root 5 divided by 4. See? So basically what you found for part D double I is that the minimum value of L, so L min, okay, is going to be 15 square root 5 divided by 4. Okay, and just to double check, because these exercises are a little bit infernal and hard, there it is, 15 square root 5 divided by 4. All right, awesome. And now for the last part, we need to do this thing that says two people need to carry a pole of length 11.25 meters from the passageway into the room. It must be carried horizontally. And so we need to determine whether this is possible, and give a reason. Okay? Now, this is interesting. Over here, it's worth 2 points, right? And so because it's asking for you to give a reason and see if it's possible, on the one hand, you probably have like a reasoning point of figuring out if it's possible or not. And then you have to give an argument. That is why it says give a reason. Okay, so you need to figure out a way to get both of those points. Okay, don't just put the math, also maybe put a little bit of writing, etc. Blah, blah, blah. See, it doesn't have to be long, it doesn't have to be a paragraph, but just whoever's evaluating you needs to understand your thought process. Okay, that's the whole point of method points and all the and reasoning points and this or that. They have to understand what you're thinking of. Okay, they have to be able to follow that. So for this last part, really, we just need to understand a lot of context. See, we need to really sort of absorb. Okay, we need to absorb a little bit, like everything this exercise has been throwing at us lately. Okay, so let me make a little bit of space. So here we will be working for party. Okay, so first things first. In this exercise, we did find out at some point that you have a minimum or maximum when alpha equals arctan 2. We discovered that right there, it was a minimum. Now alpha, let's recall, alpha is this angle. So really what you're finding, okay, is that that is the minimum angle for you to be able to have this line AB. And that right there is very important for you to understand. So we just discovered through all of this exercise that when alpha equals arctan 2, this line AB can exist. So that is the minimum angle you need for this like sort of side to exist. And so you also discovered that when that happens, L minimum, right, equals 15 square root 5 divided by 4. See? That is the distance of AB. Like the minimum length it ends up being in order for that angle to like sort of exist or whatever. See? So basically, now two people show up and they say, okay, we need to pass through this passageway. Right? And into this room. And so they're carrying a stick that is 11.25 meters long. And so they're carrying this stick that is 11.25 meters long. And basically, they need to put it into the room. And so they're going to start shifting it slowly, and they're going to try to reach a scenario where you have a horizontal line, because they do say that you need to carry it horizontally. Now, evidently, at some point, it will also end up like line AB. It will be superimposed on it. It will be right on top of it. And so at some point, what you really need to evaluate is, okay, so this pole, when it reaches this position, is it slightly longer than what it should be? Okay, so in other words, what I'm saying is that if it's, for example, larger than 15 square root 5 divided by 4, it won't fit. That's what I'm telling you. That is what I just drew over here. But if you end up with a pole that's a little bit shorter, so for example, a pole that is, I don't know, until there, so here's a bunch of like extra space that they can take, then you would say if it's actually less than the L min, so less than this, well, of course it will fit. Okay, so that is the sort of mentality we need to go over. That is what we're facing right now. Now, they did tell us that the pole, so x, right? So x for pole, I say x because it's the example I used here and here, see? So for x, the pole, we established that it is 11.25 meters. Now, and this just gets very sort of like creative and it's very specific, but once you realize the approach, it turns out to be very friendly. So you know that the pole is 11.25 and you need to be able to compare it to, okay? You need to be able to compare it to the 15 square root 5 divided by 4. You need to. There's no other way. Like, and because you don't have a calculator for this paper one, because you don't have a calculator, you need to find a way in order to make them comparable. So how the heck do you compare 11.25 to 15 square root 5 divided by 4? How the heck do you make these two numbers more similar to each other? So on the left, you have like more of a normal number. It's a decimal, like whatever. See? On the right, you have this crazy square root. Now, this square root, can you simplify it? No, you can't. And so on the one hand, the one approach that you can sort of eyeball, and it, to my knowledge, it would be good enough, you would think about, okay, what are the perfect squares that are between this? And so between this, you have the perfect square of 4, and you have the perfect square of 9, because here you have 2 squared, here you have 3 squared. And so from just that, you can sort of approximate and say, okay, yeah, I mean, square root 5 is pretty much, it's less than 3. Okay, you can establish that it's less than 3, and that's probably good enough. So you can call this like, I would say it's like 2.25 or something. See, just to make the math a little bit easier, I'm just gonna go ahead and say that it's 2.5. See, realistically, you would approach it in a different way, but you can say that, okay, it's pretty much 2.5, so you can say 15 times 2.5 divided by 4. You still have 11.25 on the left. You can end up with, this would end up being, well, of course, you're an HL, so you do quick maths faster than this boomer, but you do end up with 30 plus 7.5. So you end up with 37.5, if I'm not mistaken. Claro, that makes sense, yes. Divided by 4. And so which one is bigger, 11.25 or 37.5 divided by 4? Now you know that this divided by 4 has to be less than 10 because 40 divided by 4 is 10. And so this has to be 9 something, okay? I'm sure you can do the math on your own and you'll figure it out, but basically you would end up concluding that 11.25 is actually bigger, okay, than like around 9, okay? And so that would be your justification to say that the pole would basically not fit, okay? You would be discovering that the 11.25 is a little bit bigger than the 9, okay? So that is one argument, and the main reason that would apply for your answer is this right here. So make sure you write it somewhere so that the guy evaluating you or the person evaluating you knows what's going on. So that is one way to do it. Now, I'm going to show you one more way to do it because I know some of you are probably not convinced by this. See, you're probably telling me, you're estimating, you're eyeballing, I don't like it. Although it's good enough, I'd rather show you another way because why not? We got the time. See, and you're still sticking around, you're still in this video, so hey, might as well learn something. See? So, the other sort of approach that you can do, okay, which starts from the same sort of like thought process. And so it starts from the same thought process because essentially what is troubling you in order to compare these two square roots, okay, is that you have a square root 5. And so it's just hell annoying, like what do you do, etc. See? And so try to replicate the number on the left to be as close as possible to the number on the right. Okay, clearly making it the other way around, we ended up putting that square root 5 was around 2.5, which is not even close. It's actually like 2.2, I think. But, so I lost my train of thought for a second, but essentially you either try to make this one more similar to that one, or you try to make that one more similar to this one. So now I'm going to show you that alternative, making the 11.25 as similar as you can to the one on the right. So one thing you can sort of notice is that here it's being divided by 4. So that means you can take the 11.25 and amplify it by 4 over 4, right? This is legal because amplifying or multiplying by 4 over 4 is the same as multiplying by 1. And if you multiply any number by 1, nothing is going to change. 4 over 4 is the same as 3 over 3, is the same as 2 over 2, is the same as 1 over 1. It's all just 1. Okay, you are multiplying by 1, nothing is really changing. So 4 times 11.25 gives you 45. So look at that. So up top, you end up with 45 divided by 4. So now you're comparing 45 divided by 4 to 15 square root 5 divided by 4. See? So now you get a little bit closer to comparing it. Up top in the numerator, you have a 15. So how can I try to get that 15? Well, here, you know that 45 has a multiple of 15. So you can actually put it as up top, ¿cierto? 15 times 3 divided by 4 versus 15 square root 5 divided by 4. And now the last thing you need to try to make it comparable is this 3 to the square root 5. So, well, this 3 is actually pretty convenient because, well, square root 9 equals 3. And so that is a little bit more of a big brain move, but what you end up comparing is 15 times square root 9 versus 15 times square root 5. And so you can immediately say, well, because square root 5 is less than square root 9, you know for a fact that the number on the left has to be bigger, because the only thing that is different from both of these numbers is that the one on the left has a square root 9, while the one on the right has a square root 5. Which one is bigger? Square root 9. So the one on the left has to be bigger. Another important thing to mention, I suppose, is that it is multiplying in the numerator. If it were multiplying in the denominator, then yeah, a bigger number in the denominator makes it smaller. In this case, it's a bigger number in the numerator, so it's going to be a bigger number in total. See? So that would be your sort of argument. Guys, I did forget to mention, in order to get full credit, make sure that on this step here, okay, just to show that you understand your thought process and that you understand what you're doing, on this step here, you say the pole could not, right, pass horizontally. Which is really the same that I put over here. Like, if it's this, it won't fit. If it's this, it will fit. Make sure you write something like this. Okay, I was checking the mark scheme because I do want you guys to get like full credit. And so basically, this mathematical sort of argument is 1 point. It's your reasoning point. But the other point is literally like concluding what that means. Okay, it's giving you 1 answer point. All right. It's not so different when you find your p-value and this or that, and then you need to conclude the test. The same idea happens here. So this is the logic that you're following, and you do need to show you that you understand what this means. It means that the pole cannot be carried horizontally from the passageway into the room. So make sure you do that. I forgot to mention it, so it might look a little bit awkward in the editing, but I do want you guys to know because, yeah, whatever, okay? So that is another sort of argument that you can use for part E. I think both approaches work, and we ended up doing it all up top. I don't know why I put this E down here. So, ladies and gentlemen, that would be for number 11, and I will say that number 11 is pretty crazy. Okay, there's a couple things you just have to sort of know. I think the biggest thing that you gotta, like, really conceptualize is this whole max or min thing, and also, worth mentioning, this stuff right here. This stuff right here is huge, and without its knowledge, you actually can't move forward. So remember, in trigonometry, you only care about the proportions. If they're giving you one, use it, and use the friendliest version. Hopefully have your adjacent equal to 1, or whatever. See, ideally have something equal to 1 if you can pick the proportion. See, or smaller numbers better. That's pretty much it, okay? And last but not least, and this is more of a general sort of tip, this exercise had a lot of situations where they told you show that, see? And so with all these show that's, okay, you can actually skip a lot of these steps. Now, if you skip a lot of these steps and parts, there's a bunch of points that you're missing out on. That is true. But if you're running low on time and you realize that you have an exercise with a bunch of show that's, you can actually skip over to, for example, part DI. See? So part DI actually needed like nothing that you needed to do from part C or B or A. All you actually had to do was use all the show that information. Okay, so this, you know that you have a maximum here, you know that the double derivative gives you that. You can just sort of like plug in, see? I mean, literally, think about it. For part DI, all you had to do was say, this is greater than 0. Easiest 2 points of your life, see? For this minimum, well, you just gotta plug in the fact that you have alpha equals arctan 2 into this guy right there. So this is all straight from the exercise, nothing new coming out, see? So really watch out for that kind of stuff if you're running low on time. Otherwise, that tip doesn't really apply, okay? So, enough has been said. Definitely enough has been said for this exercise. It was pretty crazy, but I'm proud of you for trying it because, I mean, it's literally worth 19 points. Like, come on, are you kidding me? This part is worth 7. This part was violent, you guys. It was nutty. Anyways, good job. I'm proud of you. I'll see you around.